so far we have only talked about the fundamental voltage that is available from the converter. Now, in addition to the fundamental voltage, the switching action in the converter also produces higher harmonics. Okay. So, in this expression, if you see the VAOT, that is the voltage produced, the pole voltage produced is m sin omega t into Vd by 2 plus Vd by 2. This is the voltage produced from the half bridge, but there are some higher harmonics here apart from this. This happens due to switching action, and these higher harmonics we will try to see what are these harmonics, where are they present, like that. Okay. So, suppose in Fc is the carrier frequency, that is the triangular frequency is Fc, and F1 is the modulating frequency or the reference waveform frequency. Say for example, the modulating frequency can be a 50 hertz reference waveform, and the carrier frequency for example can be a 10 kilohertz triangular waveform. So, we define a term MF, where MF is equal to Fc divided by F1. So, it is the ratio of the frequency of the carrier to the modulating waveform. So, MF the harmonics in sinusoidal PWM, they reside around MF, 2MF, 3MF, like that. So, this is the position of the harmonics in the harmonic spectrum. So, the harmonics will reside. So, suppose if you if your Fc is equal to 10 kilohertz and your F1 is equal to 50 hertz, then the MF value is equal to 200, and so the harmonics will reside at 200, at 400, at 600 times the fundamental in the harmonic spectrum. Now, apart from, so this is the main harmonic that exists, but we also have side bands that exist at JMF plus minus k, these positions. What are the values of j and k? If j equal to 1, k equal to 2, 4, 6, and if j equal to 2, then k equal to 1, 3, 5, etc., which means in general if j equal to odd, k equal to even, and if j equal to even, k equal to odd. How does this come? If you want to do the really mathematical analysis, it comes from the analysis of the Bessel function. We are not going to deal that in this course, and interested students are you can see some other books and can find out how exactly this formula is derived. What is important here is to see the position of the harmonics, because we will come to that, because this is how, if you are designing a filter, it is important where is the corner frequency of the filter at the output of the converter. Okay. So, this waveform here shows the position of the harmonics in the harmonic spectrum. So, suppose this is the on the top here, this is the VAO voltage waveform, okay, and you can see this varying between 0 to 600, and in this case we have taken MF equal to 21. Okay. So, we expect that the harmonics will reside around MF, 2MF, 3MF, etc. even before we go into the harmonics, let us first see that what is the fundamental voltage inside this. So, we know that VAOT is m sin omega t Vd by 2 plus Vd by 2. So, here we have taken Vd as 600 volt, m is equal to 0.98. So, the fundamental voltage is 600 into 0.5 into 0.98. I am putting here the peak fundamental voltage is equal to m times Vd by 2, that is 600 into 0.5 into 0.98, which is equal to 294 volts. That is the peak fundamental voltage out of the half bridge converter. On the lower, on this curve, this is the harmonic spectrum. Okay. This curve here shows the harmonic spectrum, and the 0th harmonic, that is the DC, as expected the DC is equal to Vd by 2. We have seen it here, the DC is equal to Vd by 2, and so it must be equal to 600 by 2, that is 300 volts, which is here. This is 300 volt, it is shown as a percentage of fundamental. So, the fundamental voltage here is taken as 100%, which is equal to 294 volt, and which is obtained also from simulation 294 volts here, 293.8, which is almost equal to 294 volts. So, this one, this bar here, this bar is corresponding to 294 volt, which is at harmonic order 1, that is the fundamental is taken as 100% and its magnitude is 294, and therefore, the DC is slightly, because the DC is 300 volt. So, this value is 300 volt here and this value is here 294 volt. Okay. So, this is the DC is 300 and the peak fundamental is 294. Now, what about the harmonics? The harmonics reside, there will be side bands. From the previous formula we have seen that it is if j equal to 1, k equal to 2, 4, 6. So, therefore, side bands will exist as 17, 19, 21, 23, 25 like that. So, this is the 19th harmonic and this is the 17th harmonic like that. So, this is the place where the first band of harmonics exist, and then there is also harmonics and its side bands around 2 mf, around 3 mf, around 4 mf and like that. We are not very much concerned about the peak of the harmonics, because in any case we are going to filter out these harmonics using the, for example, a filter at the output of the converter. So, in order to determine the corner frequency of the filter, it is important to know the position of the harmonics. Okay. So, that is why we are more concerned about the position of the harmonics rather than its amplitude, because in any case the filter will filter out these harmonics. So, for example, if we see, if we try to plot the gain plot of the filter, we can have a filter of like this. This is the gain plot of the filter, okay, where this is the corner frequency of the filter. So, if we choose the corner frequency in a clever way, then we can make the gain plot in such a way that for all the harmonics here, the filter, the gain is 0 at the harmonic frequency, and all the higher harmonic frequency the gain is 0 or less than 0, or the gain is 0. So, therefore, the filter will get rid of all the harmonics present. So, if we choose a higher and higher MF value, then the filter frequency can be pushed further right hand side. For example, we can push the filter if the MF, if the first band of harmonics. So, let us take an example. That this is the fundamental and there are harmonics which are present here, and then there are second harmonics like this. So, we can design our filter such that the corner frequency is well ahead of the first band of harmonics. In another case, if we have a converter where the fundamental is here, but the harmonics are here, then the filter corner frequency can be set here. Earlier the filter corner frequency was here, now it is here. So, where this is the harmonics axis, frequency axis, and this is the amplitude. So, the filter corner frequency can be shifted if the harmonic, if the switching frequency of the converter is increased, and if we do this, the size of the filter, because the corner frequency, if you shift towards the right, the size of the filter will go down. And we can also choose, if this is for example for a second order filter, we can also choose third order filter or more, so that the slope here will change. That is also another option. Anyway, what I want to say here is that the position of the harmonics is important, because the filters will take care of all the harmonics. So, from the harmonic point of view and from the filter point of view, the value of MF should be very large. Larger is the value of MF, smaller will be the size of the filter, because you are pushing the harmonics right, more and more right in the harmonic spectrum. On the other hand, the increased value of MF causes more losses in the converter, because the switching frequency is increasing in the converter. Why does the switching frequency increases? Because now the triangle period will go down and there will be more number of switching happening in the converter. So, usually we say that for low power rating, a value of, for low power rating, for example within 5 kilowatt power rating, the switching frequency of 20 kilohertz, 40 or even 50 kilohertz is quite acceptable. Whereas, for high power applications, say in the megawatt level or in the gigawatt level, the switching frequency of the converter has to be sufficiently low. So, you can have converters where the switching frequency is less than 300 hertz, 200 hertz, etc. But that will impose a lot of restriction on the filter design, because the filter will then become very bulky. So, we go with other possibilities, other technological possibilities, one of them being the introduction of multi-level converters. We will see that later in the course. Apart from that, what are the values of MF that we should maintain? It should be an integer, MF should be an integer, because otherwise sub harmonics will be produced. So, synchronization is needed, synchronization between the sine wave and the carrier wave. Okay. So, MF must be an integer and it should be an odd value, so that no even harmonics are produced, and it should be an odd multiple of 3 to maintain the 3 phase symmetry. These criteria for MF is actually valid when MF is quite low. For example, like MF up to 21, these criteria here which I have mentioned here, it is valid. For large values of MF, these we can relax these criteria. Okay. It is not necessary that MF must be an odd value, because suppose if the value of MF is 400 or 500, then this criteria can be relaxed a little bit. Now we go into something which is the third harmonic addition.